right? Raoults law, it is under the topic when we have liquid and liquid solution. Okay, so we are going to see liquid solution, and in that we are going to learn about the Raoults law. So after Henry's law, we have also done the application. So after that, please write. Before going towards those Raoults law portion, you have to understand first of all a concept that is known as vapor pressure. Okay, so this will be our main idea in the whole lecture: vapor pressure. And vapor pressure, it is an important topic to understand. So what is vapor pressure? See, if you have a container of water and you put a lid over it and leave it overnight, then in the morning you see that lid. Okay, so when you see that lid, you will see some water droplets on the top of the lid, right? Yes or no? Correct, guys? Hafsa, Deborah, Mariam Khatun, Shahid, tell me. Hanji, you have water here, and you kept it overnight, and then if you see the lid, then you will see some water droplets. Yes or no, guys? Please tell me.
Yes.
What about others? Deborah, Hafsa, Mariam Khatun. Hmm? Am I audible, guys? Deborah, Hafsa, Mariam Khatun, please tell me.
Yes, sir.
So you understood what I said, or you did not understand what I said? Yes, Mariam Khatun. Mariam Khatun, are you able to understand what I'm trying to say? Sorry? What about others? Hafsa and Deborah? So why you are not answering, guys? Hafsa, what about you? Hafsa, am I audible? Hafsa, are you there in the class or you're not there in the class?
Yes, sir.
So you understood what I said?
Yes, sir.
So why you are not replying, guys? Now, obviously, where does this water comes from? This water is obviously coming from the water that is present in the container. Now, water in each and every temperature, it will evaporate. And when it evaporates, it will get converted to vapors. When these vapors, which are gaseous molecules, they will be traveling very fast. They hit the surface of the lid and then they get condensed to water. Now, what does it mean? It means that if we have any liquid, there will be some vapors of that liquid. If I have any substance in liquid state, there will be some vapors above that liquid of the same substance. If I am having H2O in the liquid, that means the liquid is H2O, then you will be having H2O vapors above the liquid. And these H2O vapors are obviously gas, and gas has the property of applying pressure on the sides of the container in which it is held. That particular pressure is known as vapor pressure. Okay, so please write what is vapor pressure. The partial pressure, of vapors in equilibrium with. What I am saying in equilibrium, because these vapors will be coming from the liquid, and when this vapors they strike the liquid, but then again it will get converted to in the liquid state, and it will be getting converted to the liquid state. So there is an equilibrium between evaporation and condensation happening at the surface of liquid. So the partial pressure of vapors in equilibrium with the pure liquid at a given temperature. And that is the vapor pressure of that liquid. Obviously, if you increase the temperature, then what is going to happen? Then if you increase the temperature, then more and more vapors will be formed. More and more vapors will be formed. So this is vapor pressure. Now, write factors affecting vapor pressure. Factors affecting vapor pressure. First of all, we have the nature of liquid. Now, obviously, you must have seen that liquid such as water, it takes time to evaporate. But if you have petrol or some kind of flammable oil, or even if you have, for example, ethanol that is present in deodorants and things, right? So they get vaporized very easily. That means they get converted to vapors very easily. That is why the nature of liquid is very important. And how does the nature of liquid affect? What should we see in a liquid? So please write liquids with strong intermolecular force of attraction have low vapor pressure. Have low vapor pressure. Second point is temperature. So obviously, vapor pressure of a volatile liquid. Volatile means that means any liquid which gives you vapors. Okay. For volatile substance, for volatile substance increases with increase in temperature. Another important term that you have to understand is the boiling point. Boiling point. All of you understood vapor pressure? Yes or no? Please tell me. Deborah, Hafsa, Mariam, Saad, and Shahid. Right, boiling point. The temperature at which vapor pressure of a liquid is equal to atmospheric pressure. Equal to atmospheric pressure, or in some cases you can write external pressure because that is the external pressure here. External pressure. So obviously, if there is large pressure, if there is large external pressure, then it is going to take a larger amount of heat. It is going to take a larger temperature to make the vapor pressure of liquid equal to the atmospheric pressure or the external pressure. And that is why you will write here in pressure cooker. Due to high external pressure, due to high external pressure, the boiling point of liquid increases, and hence food is cooked quickly at higher temperature. Another point. If the vapor pressure of a liquid is very high, if the vapor pressure of liquid is very high, then to reach 1 atm, it will require less temperature. Because we have already too many vapors, and to boil a substance, we need to reach the vapor pressure to 1 atm. That is why if it already is having too many vapors and the pressure is already high, it will be easier for it to reach the boiling point, that is 1 atm. So at boiling point is the temperature at which the vapor pressure is 1 atm. So you can directly write boiling point is inversely proportional to vapor pressure. आइए बैठिए आप लोग, है ना, सुन के चले जाइए बस, ठीक है, बिकॉज रिप्लाई तो आप लोग कर नहीं रहे, सवाल पूछने से क्या फायदा. अदरवाइज माय होल टीचिंग मेथड इज क्वेश्चनिंग एंड देन आई एम टेकिंग आंसर्स, लेकिन आप लोग जवाब ही नहीं दे रहे, क्या ही बात है. If I don't get a reply, then what's the reason of asking questions? After this, please read Raoults law. तुरंत खत्म हो जाएगा, आज तो चैप्टर खत्म कर दें हम बैठे बैठे. राइट, नेक्स्ट Raoults law. Raoults law says that but for a solution of volatile liquid, for a solution of volatile liquid, the partial vapor pressure, the partial vapor pressure of each component is directly proportional to its mole fraction. Which means in a liquid solution, I have two components, A and B. So the partial pressure due to A will be directly proportional to its mole fraction, and the partial pressure due to B will be directly proportional to its mole fraction. Thank you. Now we'll put up a constant here, and we call that constant as P naught A, chi A, and PB will be equal to P naught B, chi B. Now what is P naught A and what is P naught B? You can listen here very carefully. When chi A it is equal to 1, when chi A it is equal to 1, chi A is equal to 1, it means we have only A in the solution. That means we have pure A in the solution. And when we have pure A in the solution, whatever the vapor pressure is because of A. So you can see PA is equal to P naught A. When chi A is equal to 1. That means what is P naught A? P naught A is the pressure when the mole fraction of A is 1, when we have only pure A. P naught A is the pressure or the vapor pressure when we have pure A. Similarly, P naught B is the vapor pressure when we have only B in the solution and there is no A. After this, please write P naught A and P naught B are the vapor pressure of pure A and B respectively. Pure A and B respectively. Now, the total pressure of the solution will be equal to pressure due to A, that is PA, plus the pressure due to B, that is PB. And PA is equal to, we have seen P naught A chi A plus P naught B chi B. So this is the formula for Raoults law. This is the, I would say, the definition of Raoults. So if you write Raoults law, what is Raoults law? Write the mathematical expression for Raoults law. This is the mathematical expression for Raoults law. Now, there is a specific form of this particular Raoults law that we are going to use for numericals. Please write for numericals. Now in numericals, generally you must be given the mole fraction of the solute, and we know chi A plus chi B is equal to 1. So chi B will be equal to, I should say chi A is equal to 1 minus chi B. Why I have written in the form of chi A? Because if chi B is given, you can already determine what is chi A. Okay. Now, next thing is that we will plug in this chi A in the main equation. That is the mathematical expression of Raoults. So P total is equal to P naught A into 1 minus chi B plus P naught B chi B. P naught A multiplied by 1 will be P naught A minus P naught A into chi B will be P naught A chi B plus P naught B chi B. Now from here we can see we have chi B and chi B common. So I can write this as P naught A minus, here we are having minus, so it will be P naught A P naught A minus P naught B minus P naught B into chi B. Okay, so this is one expression that you can write. P total P naught A minus we have taken chi B as common. P naught A is minus, P naught B is plus here. So P naught, if I have taken minus chi B as common, then P naught A will be minus, and this will be also, this plus will become minus. Huh? So this is the expression that we are going to use for numericals. Those who have not written, please complete. Right. In some of the questions, we will be asked to find out the composition in vapor phase. Is right, composition in vapor phase. What is composition in vapor phase? Simply speaking, if I have a solution here, okay. So let us suppose we have solution here. Now here we have A and B, both of them. Here we have A and B, and A is present in chi A, and the amount of B is chi B here. Okay, this is the mole fraction of the composition of the liquid phase. This is the composition of the liquid phase. Now, when I talk about the vapor phase, please understand. Here, let me suppose we have white for A, and this red part is for B. Now, in vapors also we'll be having some B molecules and some A molecules. Okay. Now, now we have already seen mole fraction, that is chi A and chi B. Okay. So what I'm writing for vapor phase, Ya and Yb are the mole fraction of A and B in vapor phase. Okay. Ya and Yb is the mole fraction of A and B in vapor phase. Next, we see here. If I talk about the aim, the partial pressure of A, then partial pressure of A will be equal to the mole fraction of A in the vapor phase multiplied by the total pressure according to the Dalton's law of partial pressure. and the Pb will be equal to the mole fraction of B in the vapor phase multiplied by P total. Now, how you can get P total? We have already seen the Raoults law. And what is Pa and Pb? Pa and Pb you can get from the vapor phase. You have already seen Pa and Pb. Pa is equal to P naught A chi A, है ना? And Pb is equal to P naught B chi B. And chi A and chi B are in the liquid phase. Ya and Yb are in what? In the vapor phase. So this is the expression that you are going to use if they ask you any questions regarding the vapor phase. And especially there is an example in NCERT. Wait a second, let me tell you the example. Example 2.5. Example 2.5. In this, you have to calculate the mole fraction of component in the vapor phase, as well as you have to calculate some other thing related to the liquid phase. Okay. This is the only question, and also this question has not been asked in board anyway. Composition of vapor phase has not been asked in boards till now. See, right next, that is the relationship or Raoults law and Henry's law. There is a relationship between them, and both of, if you say Raoults law, then Raoults law it is a special case of Henry's law. Okay, so please write Raoults law and Henry's law. Raoults law and Henry's law. Now please see what is Raoults law. If I take in the case of solute, then the vapor pressure of solute it is equal to P naught B into pi B. If I take the Henry's law, then Henry's law it is equal to P is equal to KH into pi B. KH into pi B. Now what is P naught B? P naught B it is the vapor pressure of pure A. Vapor pressure of pure liquid A. Now, obviously, if the P naught B is higher, that means the vapor pressure of pure A is higher. That what is there? There are more vapors of pure A. We will have more vapors of pure A. That means pure A does not want to be in liquid phase, rather it wants to be in gas phase. And that is why you can say its escapability or escaping tendency is higher. Its escaping tendency is higher and its solubility is lower. And similar is the case of KH. KH directly tells you about the escaping tendency of gas. It tells about the escaping tendency of gas. KH of a solution, if it is higher, then its solubility, we all know it is low. So actually, Raoults law is nothing but it is Henry's law. It is Henry's law only. But in Raoults law, we have both of them are liquids, and Henry's law is for any volatile substance, and Raoults law it is a special case of Henry's law, in which the KH is replaced by P naught B. The KH is replaced by P naught B. So please write here. Raoults law is a special case of Henry's law, in which KH becomes equal to P naught B. Right, next. Ideal and non-ideal solution. So in this, first of all, we are going to look at the ideal solution. No. A solution which follows Raoults law over entire range of concentration, it is known as ideal solution. So what will ideal solution do? It will follow, the ideal solution follows Raoults law or rather I should say over entire range of concentration, entire range of concentration, over entire range of concentration. In Raoults law, see Raoults law is P total is equal to P naught A chi A plus P naught B chi B. So we can get the pressure, we can get the pressure of vapor pressure of a solution using this formula, in which we can do calculation. We can calculate it, or what we can get the P total using a measuring tool, a device. We can use a device and we can experimentally. There are two ways of getting any values in science. Either you can use a calculator to calculate it, or you can use a device and you can measure it. If the device is very expensive, we generally try to find out a formula in which we can do some calculation and get the exact value, and we don't need to use the device. The device is very expensive. Okay, but that particular expression or that particular formula should be working at all the different conditions. Okay, so if a solution follows Raoults law, then whatever calculation you have done, you will get some pressure. And when you're using the device, you will get that particular pressure. And since it follows Raoults law, and both of these will be equal. That means generally what we say about ideal solution is that the pressure that is observed, that means in the device, is equal to the pressure that is calculated by the Raoults law. So P observed, it is equal to P calculated. P observed is equal to P calculated. Now, this can only happen if, please write, liquids with similar intermolecular force of attraction. Intermolecular force of attraction form ideal solution. When we have similar intermolecular forces of attraction. For example, examples are important, please write. You have benzene. Benzene, it is non-polar, and toluene. Not much difference between benzene and toluene, only increase of one carbon atom. Similarly, normal hexane and normal heptane. Both of these are liquids and both of them are forming ideal solution. Similarly, chloroethane and bromoethane. Both are equally polar and both have similar intermolecular force of attraction. That is why they form ideal solution. Next is characteristic of ideal solution. This is something that you have to remember. Characteristic of ideal solution. Since the intermolecular force of attraction before mixing is similar to that of after mixing, that is why we don't require any energy on mixing them. Also, because both the force of attraction are equal, it will not even give any energy. So delta H mix will be completely equal to 0. Second point, if I talk about the volume of the mixing, that what will be the volume after mixing, then volume after mixing will also be equal to 0, because there is no change in intermolecular force of attraction between A and B. So however, whatever the intermolecular force of attraction of A was, it is equal to B, and after solution, when we mix them, then also it is the same. That means the gap between A and A, B and B, and A and B is all same. So when the gaps between the molecules are same, the volume is neither going to increase nor going to decrease. That is why it is going to be 0. Delta V mix is also equal to 0. There are two other things that you can write regarding delta G and S3, right? See, these are not important for your board examination. Those who are preparing for NEET or something, delta G of mixing will be equal to negative, and the entropy of mixing anything is always positive. So delta S mix will be equal to positive. So entropy increases when we are mixing them. Now this is the case of ideal solution. Okay, this is the case of, till here it is important for what? Till here it is important for the board keeper. So when they talk about write the differences between ideal solution and non-ideal solution, then you will write three things. First of all, follows Raoults law. For ideal solution, you will write follows Raoults law. Then you will write delta H mix is 0, delta V mix is 0. If you want to write anything else, you can write P observed is equal to P calculated, or you can write this as the delta P is equal to 0. Delta P is equal to 0. That means the vapor pressure before mixing and vapor pressure after mixing is also equal to 0. There is no change in the vapor pressure. Okay. So this is something that you are going to write. This is something that you are going to write for ideal solution. After this, please write non-ideal solution. Second is non-ideal solution. So obviously, in non-ideal solution, we can write it does not follow. You're writing the point. Does not follow Raoults law over entire range of concentration. Over entire range of concentration. So obviously, the P that is observed in the device will not be equal to the P that is calculated using Raoults law. P that is calculated using Raoults law. And also that is why what will happen, the delta P, that means the pressure after mixing and before mixing will not be equal to 0. Will not be equal to 0. So from here you can write a few characteristics. First of all, about delta H mix. So very easy to remember things. Delta H mix will not be equal to 0. Second, delta V mix will not be equal to 0. Now from here we can only write 2 points. We cannot write delta G because now if it is not equal, then there are two cases. If they are not equal, then there are two cases. So that we will discuss that now. Types of non-ideal solution. Right, next. Types of non-ideal solution. So there can be only two cases. The first case, sorry. If they are not equal, then either the observed vapor pressure is greater than the calculated vapor pressure. So if I talk about delta P, then after mixing, the pressure has increased. So delta P will be positive, right? Before it is greater now. So what is happening after mixing? That means after mixing both of them, and when we are observing in the device, that pressure is greater. So delta P will be positive. And that is why this is known as positive deviation from Raoults law. This is also known as positive deviation. Also known as, it is known as positive deviation only. Positive deviation from Raoults law. Okay. And the other case that we can have is the P observed that we have, it is less than the P calculated. In that case, delta P will be equal to negative, and we call this negative deviation. Negative deviation from Raoults law. Negative deviation from Raoults law. Now, what are the cases here? Please see. First point is that, so how the vapor pressure is increasing after we are mixing the components. When we mix A and B, the pressure can only increase if we have more vapors in the above the solution. If we have more vapors, then only the vapor pressure will be higher. We can have more vapors only if more of A and B are vaporizing. That means A and B are not mixing effectively. They are not mixing effectively. That means A and B, they will have weaker interaction. So what I can say, AB interaction is weaker than AA and BB interaction. AA and BB interaction. That is why now what is happening? A and B, they are not friends. A and B are having enmity. That is why A is getting away from B, B is getting away from A, and they are also getting away from the solution itself. Okay, so AB interaction is weaker than AA interaction. If AB interaction is weaker, that means they don't want to mix with each other. So in that case, we will have to put some energy, and delta H mix will become equal to positive. So it is endothermic process. Next point, if I talk about the volume of mixing, then the volume of mixing, please understand A and B, they don't like each other. So they are far apart. If they are far apart, they will be occupying more space. That means volume will also increase. That means positive in this particular case. In this particular case, the volume of mixing will also be positive. Next, we can also talk about the boiling point. Next, we can also talk about the boiling point. Please remember, we have said that boiling point, it is inversely proportional to the vapor pressure. Now, as we have mixed the solution, the vapor pressure has increased. That is why we can write boiling point will be lowered. Boiling point will be lowered. Next is the case of negative deviation. So in negative deviation, obviously it will be completely opposite. In negative deviation, we are getting less pressure. So less vapor pressure will be only present because if we have less vapor, we will have less vapors when A and B are interacting. And A and B are what? They are having very good friendship. They are mingling with each other. They are not letting, A is not letting B get vaporized, B is not letting A get vaporized. So everything is in the solution and we have less vapors, right? So obviously it is because of AB interaction. AB interaction is stronger than AA and BB interaction. AA and BB interaction. Next point, obviously, if they are mixing very good, the mixing is very good, and AB are interacting very well, then obviously it will release energy. So delta H mix will be negative. And if I talk about the delta V mix, now since A and B are friends, they will be close together and they are having stronger interaction. They will be close together and occupying less space. That means V mix will also be negative. Last point is regarding boiling point. If we have less vapor pressure, then the boiling point will be increased. So please write boiling point will be increased. Boiling point will be increased. Write this down. Let me know once you're done. Types of non-ideal solution. When they talk about the difference between positive and positive deviation, negative deviation, I would suggest you guys to at least remember these 2 points. It's very easy to remember, right? That first of all, or you can also remember this point. Okay. So positive deviation, delta P is positive, delta H mix is positive, delta V mix is positive. For negative deviation, delta P is negative, delta H mix is negative, delta V mix is negative. It's very easy to remember, but please remember also one more point. You cannot ignore this part. Okay, I'm not asking you to ignore this part. I'm just asking you to write these things. So it will take less time. And if they are asking the difference, 3 points is enough. They will not ask more than 3 points. You can write all the points, no problem. But I'm telling you what to write to save time. Yes, you write small things, which is going to give you marks. And also in chemistry, you don't need to write very long things. Okay. I have seen the mark schemes that is provided by CBSE for each paper, and they never have very long answers for anything. It is not English or it is not social science that you have to write lengthy answers. You have to write precise answers to what the question is asking. Now, after this, there is a topic of azeotrope, and this azeotrope is completely related with the deviations in Raoults. So when we say types of non-ideal solution, this also means deviations from Raoults will be two things. Right? So there are two deviations. So let me write it here also. It is what? It is deviation from Raoults law. Okay, deviation from Raoults law. So positive deviation, negative deviation. The two types of non-ideal solution. Now, let us say we have an extreme case of positive deviation. We have extreme case of positive deviation. Then what is going to happen? Please see. I have A and B as the component. A, it boils at, let us suppose, 150 degrees Celsius. B, it boils at around, let us suppose, 80 degrees Celsius. But when I mix them together, A and B, they have such weak interaction between them. A and B, they have such an enmity that the vapor pressure is increased so much so that when I mix them, the solution's boiling point, the boiling point of the solution, it becomes equal to, let us suppose, 70 degree or 50 degrees Celsius. Now what happened? The boiling point of the solution is lower than both the component. It is lower than both. I mean, they have so enmity. The interactions are so weak. The interactions are so weak that neither A wants to stay in the solution nor B wants to stay in the solution. Both of them are getting vaporized very easily, and they have a lot vapor pressure. The vapor pressure is very high, and the vapor pressure will be very high. It will be very easy to reach 1 atm. So in a lower temperature, we will reach 1 atm. And as soon as we reach 1 atm, it will be boiling. The boiling point of solution becomes 50 degrees Celsius. Okay. Now, both of these A and B, the components that we have, they are boiling at 50 degrees Celsius only. They're at 50 degrees Celsius only. Okay. This is the case I'm saying when we have positive deviation part. So let us suppose we don't have this type of deviation. It is an ideal solution. So A will be acting on its own. B will be acting on its own. A is not interfering with anything about B. B is not interfering with anything about A. Now, when we have this type of ideal solution, then please see what happens. When I start to heat, the temperature will rise from 25 degrees Celsius, that is the room temperature. It will slowly reach 30 degrees Celsius, 40, 50, 60, 70, and 80. As soon as it reaches 80 degrees Celsius, after that, no matter how much you heat, the temperature will not increase. Why? Because the boiling point of B is 80 degrees Celsius. And at 80 degrees Celsius, the B will start boiling off. The B will start boiling off. And when the boiling is taking place, please remember the concept heat of vaporization. Extra heat that is provided to the system, extra heat that is provided to the liquid, it is not used for increasing temperature. Rather, it is used for converting liquid to gas. It is used to converting liquid to gas, and that is known as the latent heat of vaporization. So because of latent heat of vaporization, even though you are increasing the temperature, even though you are giving more heat, the temperature will not increase. First, all the B molecule will boil off. Once B is completely over, we don't have any B in the solution, then the temperature will rise. Then the temperature will rise. It will rise 80. It was at 80. It boiled for a very long time. All the B is completely gone. We don't have any B in the solution now. We have only A, and that is why now we don't need any heat to convert anything from liquid to gas. That is why the heat will be used to increase the temperature.
Now the temperature will increase 80, 90, 100, 10, 120, 130, 140, and 150. As soon as it reaches 150, it will start boiling once more. It will start boiling once again. So when we have ideal solution, and also binary ideal solution, when we have two components, so these solutions, they boil at two different temperatures. But when we have a non-ideal solution, an extreme case of non-ideal solution in which we are having positive deviation, let us suppose here, as we took the case earlier. So when we have A and B and these are forming a non-ideal solution with a positive deviation, their extreme case of positive deviation, then their boiling point lowers down and it becomes equal to, let us suppose, 50 degrees Celsius. The complete solution is boiling at only one temperature, that is 50 degrees Celsius, and that is the definition of azeotrope. That is the definition of azeotrope. So this is, we have taken for the case of what? For the case of positive deviation, and extreme case of positive deviation. Let us suppose we have extreme case of negative deviation. A has a boiling point of 150, B has a boiling point of 80, but the interaction between A and B is so strong, so strong, so strong that when we mix them, the boiling point of solution becomes 200 degrees Celsius. Because A does not want B to leave, B does not want A to leave. B does not want A to leave, A does not want B to leave. And at this point, what is going to happen? Neither the solution will boil at 80 degree, nor it will boil at 150 degree. It will rather boil at 200 degrees Celsius, and there is only one boiling point of that particular solution. So generally, solution, when we have ideal case, they boil at two different temperatures. But when we have extreme cases of deviation from Raoults law, extreme cases of non-ideal solution, then they boil at one temperature. So we have to give this type of solution a particular name, and the name is given as azeotrope. Please write azeotropes. What are azeotropes? Please write azeotropes are solution which boil at a constant temperature. Boils at a constant temperature. Also, if they are boiling at only one temperature, so in the case we have seen where the temperature is lowered, the boiling point is lowered, it becomes 50 degrees Celsius. When it is boiling, both A and B will be boiling off, right? Both A and B will be boiling off. In the ideal case, what was happening? First B boiled. So when the boiling was taking place, we had only B as the vapor. A was only liquid. But when we have deviation, both A and B will be boiling. So we can say azeotrope have same composition in liquid phase as well as vapor phase. As well as vapor phase. Now there are two different types of azeotropes that we can have. First is maximum boiling azeotrope. Then we have minimum boiling azeotrope. Okay, maximum boiling and minimum boiling. So maximum boiling azeotrope, when the boiling point of solution, it is what? It is greater than the boiling point of both the compounds, okay? Both the components. So in this case, what is going to happen? Boiling point of
solution is greater than boiling point of both components is right shown by solutions with extreme negative deviation. In minimum boiling azeotrope, the boiling point of solution is greater than boiling point of, oops, my bad, is less than, is lower than boiling point of both components. Shown by solution with extreme positive deviation. The extreme positive deviation. We'll write the last point, that is graphs and examples. Okay, so first we will see the graph of Raoults. Someone is saying something? Yeah, please write. First of all, we'll see. Can you see it properly, please? I can't hear anyone. First, we'll see the graph of Raoults law. Okay, also, and it is finite solution. So please see, you must be seeing this graph for the first time. Okay, please see here. Now, this is for the ideal case, okay? The graph of Raoults law. At this particular point, the mole fraction of solute is taken as 0. If the mole fraction of solute is 0, you'll have pure solvent. And when we have pure solvent, its vapor pressure will be P naught A. Similarly, take the extreme case here. Here, the solute is equal to 1. The mole fraction of solute is 1. So obviously, the solvent will be 0. And whatever be the vapor pressure, that will be only because of solute. So P naught 2. Here, in NCERT, they have taken 1 and 2. So here you will have, this is P naught 2. That means the pure vapor pressure of solute. Now, these dotted lines, they tell about the PA and PB. When you are at this particular point, the vapor pressure because of the solute is equal to 0. And because the solute is not present. As I move in the rightward direction, the amount of solute that is added, the mole fraction of solute increases. If the mole fraction of solute is increasing, it means solute will be getting vapor to the vapor phase. So the pressure due to solute is also increasing slowly. And as it reaches 1, it will reach the pure vapor pressure. Similar is the case of P1. And this is the, when we are here, that means we have only and only solvent. As we add more and more solute, what is going to happen? The pressure is going to increase because the pressure of the solvent solute is more than that of solvent. So as we are adding more and more solute, the pressure is increasing. And if I add too much of solute, then it will become what? Only solute, and only solute will have a vapor pressure of P naught. So this is the case when you have ideal solution. Now, in the case of non-ideal solution, there will be two cases. दोनों एक साथ नहीं रह सकते क्या? Okay, please. When we have positive deviation, then in that case, what is going to happen? In that case, the vapor pressure will be higher. So vapor pressure will be higher. So you will have this type. This red line is for positive deviation. Similarly, the vapor pressure will be also higher for these solute and solvent. This is positive deviation. For negative deviation, it will be just lower. For negative deviation, it will be less. Okay, so this red part, this is for pressure is high. This is for positive deviation. Then you have the blue one, where the pressure is low, it is for negative deviation. Okay. I would suggest that you make the graphs from NCERT. Okay. Make the graphs from NCERT, or you take a screenshot from here. So if you make the graph from NCERT, I will give you the page number. For ideal, you have to go to page 44. In 44, and for the non-ideal solution, I think it is after 2 pages. So it will be in 40. Oh, it's later. 48, page number 48. Okay. In 48, you will get two graphs for the deviation. This we will get on 48 page number. Now, let us look at some examples, and there are a few examples. Okay, so please write it down. Positive and negative, you will get it from page number 48, and this you will get in page number 44. Right, next, in the example case, we have seen the examples of positive, sorry, we have seen the examples of ideal solution. Now write the example for the positive deviation. For positive deviation, you have some examples which are very important. And in positive deviation, phenol and aniline. Phenol, no, ethanol and water, I think that is an example which is important. Just give me a second. Ethanol and acetone, number one. Ethanol and acetone. Okay, so this is the most important that you are going to remember. Secondly, you have certain other things that you can add on ethanol, which is going to give you positive deviation. Please write ethanol and cyclohexane. Ethanol and cyclohexane. Third is you can write what? You can write ethanol and water. All of these are examples of positive deviation. Okay. Next is for negative deviation. The first example that is important, I think that is chloroform and ethanol. No, chloroform and acetone. Chloroform, that is CHCl3 and acetone. Acetone has CH3, C double bond O, CH3. CH3, C double bond O, and CH3. That is one of the example. And I think another example is aniline and phenol. Second example, both of these are in NCERT, aniline and phenol. Aniline and phenol. Third example, which has been asked previously in NEET examination, is water and nitric acid. H2O and nitric acid. What else? So I don't think you don't have anything else to remember. Okay. So these are the examples: positive deviation and negative deviation. So complete Raoults law is over. Okay, complete Raoults law is over. Again, take some homework. In text question 2.8. In text question 2.8 and in exercise, this is important. Okay, I think it has been asked many times in the board examination. And in the exercise, you will do the question number 2.16. Exercise. See, 2.14 is a theoretical question. No, so you can also write that 2.14. Then 2.14 after that, 2.16. Depending on my resolution. So what is it? What else you can do? .38. Okay, so 2.38, it uses the it has a question of write the mole fraction of a particular component in vapor phase. So in vapor phase, we have already seen for composition in vapor phase how to do that. Composition in vapor phase. Okay, so they will ask you, this is one of the examples that you need to do. 2.5. And so one thing I will just tell you guys, while you are doing some questions, you will be asked to, you have to calculate the number of moles of A and B, right? So calculate the number of moles of A and number of moles of B, given mass of A divided by the molar mass of A. In many cases, you will not know what is the molar mass of A. So please Google it. Okay. Please Google the molar mass while you are doing any calculations. If the molar mass in NCERT, they have not given the molar masses. But if you pick up and see any of the previous year questions, in each and every set of the previous year question, they have given the molar mass of each and everything, except for simple cases such as, except for